Hi class. So we left off talking about computing the R given the data presented at this table. So you should have a table filled out that looks something like this. So again, each row of data corresponds to one participant. They contribute an X score and a Y score. So we're taking the deviation from the mean for each X and the deviation from the mean for each Y. And we're squaring them, each of them, to get a sums of squares for X and a sums of squares for Y. Those values tells us how much those variables vary with itself. Okay, what's the variability of our X variable and what's the variability of our Y variable individually. Then, when we multiply the deviations together, only the regular deviations, not the squared, that tells us that SP, the sum of the products, tells us how much those variables vary together. Okay, so our R ratio is a formula that looks at how much the variables vary together over how much they vary individually. And if there's a strong relationship, then their variability together will outweigh the variability individually. Okay, so you should see something like this, which gave you an R of 0.298. I believe so. Okay, so it's a small positive correlation. 0.298 is positive, so it's a positive direction. So as X scores increased, Y scores moderately increased as well. Okay, so just to review, correlations range from -1 to 1. They must be linear related. Okay, and when there's a correlation of 0, that indicates a weak relationship or no relationship. And we compute the correlation by looking at how much the scores covary and how much they vary individually. Don't worry about the z-scores. There's something in your book that talks about that, but I'm not going to focus too heavily on how z-scores are computed with the R. Okay. There are several applications that we use in psychological research that are useful for correlation. The first is prediction. We talk about this when we get to regression. But if we know the relationship between two variables, then I can take your score on one variable and predict how you're going to perform on the second variable. This is used all the times in college selection. So based on your high school GPA, they can predict how your college GPA should turn out. Similarly with the GRE and the SAT, your SAT score usually is somewhat predictive of your college GPA. It's not always accurate. There's always some error involved in individual differences. However, this is used highly in much research. Again, you have to have that established relationship in order to do this. We also use this with validity. The next two slides discuss validity and reliability. So you should know the difference between the two of them. And you're going to hit this a lot harder in 318. But validity is a concept that looks at whether a test is measuring what it's intending to measure. Okay, so does the IQ test actually measure intelligence? Okay, well, there's some controversy around that. Does the GRE actually measure academic aptitude? Or specifically, does your statistics final actually measure those chapters that it's intended to measure? If I put chapters 1, 2, and 3 on your stats final, then that wouldn't be a very valid final, okay, because I didn't cover the material that it was intended to cover. Reliability, on the other hand, is somewhat different. It's kind of the other side to the same coin. Reliability is referring to a test consistency. So does the test provide similar responses from one test to another test? So for example, if you take the SAT twice, you'll see a pretty consistent score, unless you've done something drastic like not prepared the first time and then you drastically improved your preparation the second time. You're going to see relatively the same score. Same thing with driver's tests or say a personality measure. You're expected to have pretty reliable results. That doesn't mean that you have validity. You can have validity and not reliability, or vice versa. So these are two separate concepts. And they are not, they are exclusive. And lastly, and probably most useful, is theory verification. So when we have a hypothesis or a theory, usually based on previous research, we develop our hypothesis and we can use correlations to test whether those relationships really do hold in the population. Okay, so You want to make sure you do this with previous research. You don't just make up these hypotheses, but this is really useful for correlational research, especially when we can't do manipulations. So we can't manipulate people to be drunk in public and see, you know, what their responses are. Okay, a lot of times we just have a hypothesis and we use correlations to determine that relationship. There are several problems, though, you have to be cautious of when you're using correlation. The most important is causation. We cannot infer causation from correlation. All we're looking at is a relationship. The only way you can infer causation is if you are doing a manipulation, an experimental design. Okay, there are many reasons X and Y may correlate, and when you're only looking at two variables, you're discounting all other possible factors that could be influencing that relationship. So take, for example, ice cream and crime. They're very highly positively correlated. So as ice cream sales increase, so does crime. So if we made a statement that said ice cream causes crime, that would be incorrect, invalid conclusion. And the reason why is because there's a third variable, and that's temperature. So as temperature increases, ice cream sales increase, and likewise, as temperature increases, crime increases. Okay, so you have to look behind that correlation and ask yourself if there is, in fact, other variables that are influencing that relationship. We also want to be cautious of restricted range. This is when you infer your relationship beyond the data that you've collected. So if, for example, you're looking at the effect of, let's say, we want to look at the amount of alcohol you consume and your behavior. Well, if you have between 0 and 3 drinks, you might see a positive relationship between drunkenness in public. However, if that's all you collect and you conclude that there's a positive relationship, you don't know if that relationship holds true for people who have 4, 5, 6, even 10 drinks. Okay, so you want to make sure that you make your conclusions of your relationship only in regards to the data that you collect. Okay, you don't want to assume what the relationship is outside that context. Outliers have always been a problem in every statistic we've computed, especially like the mean and standard deviation, and they affect our correlations as well. Okay, we call them corpses in the sample sometimes because an individual who just answers 0 on everything, then they become that 0 data point, and it kind of weighs the line down to them. So it makes the relationship inaccurate. Okay, so you want to keep an eye out for outliers, and some advanced statistics will show you some methods you can do to handle outliers. And lastly, but probably most importantly, is the assumption of linearity. Okay, we want to make sure that the Pearson correlation has a linear relationship between our two variables. There are other types of correlation coefficients that can be applied to curvilinear relationships. However, that wouldn't be the Pearson. So, for example, the anxiety and test performance, it shows a normal curve, a normal bell curve. So that means that as anxiety increases, test performance increases. It's actually good to have a little bit of test anxiety, but only up to a certain point. Once you get too much test anxiety, your test performance actually goes down. So it forms a normal bell curve. And if you try to calculate a correlational coefficient based on that data, you'll find a correlation of 0. So you're not going to actually capture that relationship if you try to apply a linear correlation to a curvilinear relationship. Okay, the best way to test this assumption is to examine a scatter plot. So you can square correlations, square your R, and you will get a measure of effect size. Remember R squared? R squared is the proportion of variance that is due to your effect. So R squared in this instance is the same thing. It's the proportion of variance, and it's the proportion of variance that's shared by the relationship. Okay, so it's the same thing that we have already discussed about R squared, and you can interpret the magnitude of that effect the same way as before. And lastly, we can also conduct hypothesis testing just as we have with every other research design. So we can determine whether or not there's a significant relationship, whether or not that correlation, that R, is large enough to be determined significant. So to do this, we're going to find our critical value. We have another table in the back of the book, the R table. All you need to know is degrees of freedom and alpha. Your degrees of freedom is going to be n minus 2 because you lose 1 degree of freedom for each variable. And then you have alpha and you look up your critical value for that test. And once you calculate your correlation coefficient, you determine whether or not that value is large enough to surpass the critical value. So if it's a two-tailed test, we have our rho, that's our population for R. The correlation is expected to be 0. There's no relationship. Okay? Or the alternative says it's not 0. Could be a negative relationship or positive. If it's a one-tailed test, then our correlation is expected to, for our alternative, be greater than 0 or less than 0. Okay, so this is very similar to what we've already been studying. We're just applying it now to the population of correlations. Okay, so that rho signifies the population coefficient for a correlation. So here's an example. We're looking at a study of MRI scans to count the number of neurons in the brains of 38 college undergraduates. The undergraduates took an IQ test, and we want to determine if there's a relationship between IQ and the size of a person's brain as measured by the number of neurons. Okay, so each person, each of these 38 students, contributed 2 scores. They have the number of neurons in their brain, and they have their IQ score. Okay, so the following data is going to give us calculations that are going to determine our correlation. Okay, remember our correlation is our sum of products divided by the square root of our sums of squares x times our sums of squares y. So take a look at this data here. Notice we don't have our individual data points. So like you calculated the R in your table on your worksheet, we don't have our individual x and y's. So you're going to have to calculate your sums of squares and your sum of products in a different way. So on your worksheet, the ways that you calculated those values were based on the definitional formula for sums of squares. Okay, we took the deviation, we squared it, we took the products, we multiplied it and summed it. Okay, so that's the definitional way to calculate those values. However, we can use the computational method and we can get the same result. So recall the computational formula for sums of squares. In that formula, if we're looking at, say, our x, sums of squares x, that formula would be sum of x squared, this value right here, minus sum of x squared divided by n, which is 38. So you can solve for your sums of squares x by using these two values right here. You can do the same for your sums of squares y. It's your sum of y squared minus the sum of y squared divided by divided by 38. And lastly, you can solve for your sum of products, which is a slightly new formula. And that formula, it's on a previous slide, is your sum of your x and y product, which is right here on the bottom, minus the sum of x times the sum of y divided by 38. Okay, so you don't square either of those terms. It's your sum of xy minus your sum of x times your sum of y divided by 38. Okay, so go ahead and try to get those values, and if you can, solve for R. You might want to pause it here and go back and refresh your notes just to make sure that you are pretty clear on how those values are calculated, because you're going to be expected to solve for your sums of squares both definitionally and also computationally. Okay?